What is up, everyone? It's Mr. Holtz, and today we're going to continue our discussion on density. Now, so far we've looked at how density can be influenced by the variables of mass and volume and how those can influence the density of different objects. But what we're going to be doing today is looking at a couple different demonstrations that will help us compare the densities of different solids, liquids, and gases. And hopefully, by the time this video is over, you guys will have a better understanding of density and how it's incorporated in our daily lives. So let's get to it. So the first demo we'll be looking at today is we're just going to be taking these rocks and putting them in this bucket of water and seeing what happens. So we have two different rocks here. They're about the same size. This one on the right might be a little bit bigger. But as you can see, they have a little bit different texture to them. This one clearly has some holes. It's a little more porous. Kind of looks like if you took SpongeBob and made him into a rock. Whereas this is just like a regular rock that you'd find out in, I don't know, in your backyard or something. So take a minute and try and come up with a hypothesis as to what you guys think is going to happen when these rocks get tossed in water. Now, this is just tap water. I just poured it out of the sink, and it's just sitting here in this bucket. There's nothing really special about this bucket, but let's take a look at what happens when we add these. So I'm going to add this one first. All right, now it's a little dirty, so got some sand in the water, but hopefully you guys can tell it's pretty obvious that sank straight to the bottom. Okay, it made a big noise, but let's take a look at what happens with this one. Okay, now we want to make sure that this one isn't just resting on the other rock, so look at this space here, all right? You guys can see this top one is not just sitting on top of this rock, right? It's actually floating at the surface of the water. Now the reason for that is this is a special kind of rock called a lava rock, and because it has all of these pores in it, because it has all these holes, there's a bunch of empty space within this rock that's not actually made of rock material. So because there's lots of empty space, it's less dense than this rock down here. And it turns out this rock is actually less dense than water because it has so much empty space in it that it can actually float when we put it in a bucket of water, just like you see right here. All right, so now that I got those rocks out and we got a new bucket of water, the next demo we're going to take a look at is we're going to be tossing both of these cans of Coke into this bucket of water, okay? Still just regular tap water, nothing special about it. But notice both of these cans are sealed, so they haven't been opened yet. Right, we don't want to open them because then if we open them and toss them in the bucket, they'll just mix in with all the water. We won't really have a good understanding of what's going on. So what we want to do is we want to compare the density of Diet Coke to regular Coke. So take a second and try and come up with a hypothesis of what you guys think will happen when both of these cans are tossed in this bucket. Are they both going to float? Are they both going to sink? Is one going to float and one going to sink? If so, why? What would be causing that difference? So let's take a look at these. I'm going to toss the regular Coke in first. Okay. So it looks like slowly sinking to the bottom. All right, it might take a minute to balance out, but notice that it's not floating at the top. And after we had a minute of it kind of bouncing in the center of the water, it slowly sank down. So that might tell us that it has a density that's pretty close to water, but it's still a little more dense than water, which is why it's sunk all the way to the bottom. So let's take a look at the Diet Coke now. Okay, so it disturbed this one a little bit, but we can see it settling back down to the bottom again. Notice how the Diet Coke is floating at the top. Let's turn it upside down and make sure that we can try and get it as accurate as possible, right? We want to make sure none of our experimental setup is influencing what's going on. So even when it's right side up, our Diet Coke is still floating at the surface and the regular Coke is still sinking to the bottom. So we can see a major difference in density here, even though they're both Coke, right? But the major difference is this one's Diet and this one's regular. So all of the sugar that's added to the regular Coke increases the density because there's a lot more stuff dissolved in this soda than there is in this soda. So this one's not as dense because there's not any real sugar in it. All right, so this demo is going to be a little bit different because instead of testing two different solid things like we did with the rocks and the sodas using one liquid, which was our bucket of water in that case, now we're going to be using two of the same solid and comparing two different kinds of liquids. So here in this graduated cylinder, we have a bunch of water, And here in this graduated cylinder, we have a bunch of ethanol, which is a specific kind of alcohol. So you can see that I got them from these buckets back here. Okay. Now I found two candles that are about the same size. I tried to find two that were as close in size. They're made out of the same material. So these candles you guys can think of as equivalent, okay? They're this in terms of their density. So what we're going to be doing is we're going to compare the density of water to the density of ethanol using these two substances. So when I toss a candle in one, it may float or it may sink. But because these candles have the same density, they'll help us compare the densities between the water and the ethanol. So let's drop it in the water first. Maybe you guys have played with candles and water before, but let's see what happens here. So, all right, splash all over. Okay. So the candle in water looks like it's floating up at the top, which tells us that in this case, the water has a greater density, or it's more dense than the candle, which is why the candle's floating at the top. So let's take this candle over here and add it to the ethanol and see what happens in the second graduated cylinder. Okay, so that's splashed all over the place. But as you guys can see, this candle sunk to the bottom, which tells us that in this case, right, our candle was less dense and the water was more dense than the candle. But in this case, with the ethanol, the candle seems to be more dense, right? It sank all the way to the bottom. So the liquid must be less dense than the candle. And in this case, because the candle is less dense than the water, we can determine that the ethanol is also less dense than water. So if you have this alcohol and you mixed it with water, the alcohol would sit at the top because it has a lower density, and the water would sit at the bottom. So for our next demo, what we're going to be looking at is these two candles right here. Now I'm doing the best I can to show that they're slightly different heights. So if you look carefully, you'll see that this candle on the right is just a little bit taller than the candle on the left. So what I'm going to do here is I'm going to take this beaker and I'm going to put it over the candles upside down. Okay, so they're going to run out of air. But what I want you guys to pay attention to is what order do they go out in? So let's take this, we'll put it upside down and try and take note of what candle goes out first and what candle goes out second. Oh, I hope I don't take any of them out right now. All right, so let's see if we can get a good look at this. I know there's a little bit of the glare from the glass. Okay, so I don't know if you guys saw that little plume of smoke on the right over here, but the right candle just went out first. We're starting to build up some condensation on the inside, so if you see all that fog, that's what's making it kind of hard to see. And our second candle just went out, okay? So, if you followed along, the first candle to go out was the one on the right, so it's a little bit taller, and the second candle was the one on the left. So this one burned a little bit longer. Now the reason for that is because when candles burn, or when anything burns, CO2 or carbon dioxide is produced. Now, obviously, heat comes from the flame, which is why you don't really like to touch fire, right? It's not very good for you, it'll burn your skin. So what happens is that when the CO2 is being released from the candle, it's coming off really, really hot because it's being produced where the flame is. So obviously it would be pretty warm. So what happens is because that gas is so much warmer, warm air likes to hang out in the higher places, which is why if you fart a lot, you probably don't want the top bunk. So what ended up happening was the CO2 that was produced is nice and hot, and since this was upside down, the CO2 is kind of getting trapped at the top of this beaker and didn't really have anywhere to go because it couldn't escape since there's no holes at the top, or in this case the bottom, since it was upside down. So as more and more CO2 builds up as the fires continue, what ends up happening is that the CO2 is hotter than the oxygen that's already underneath the beaker, because obviously the fire from the candle needs oxygen to continue burning. But what happens is that because the CO2 is hotter, the CO2 likes to hang out higher in the beaker, and the oxygen likes to hang out lower because it's much colder, because it's not being produced from the flame, it's just at room temperature. So the CO2 builds up and builds up and builds up, and eventually pushes out all of the oxygen to the bottom. So when the CO2 level met where this candle was, the flame went out because all of the oxygen was being pushed underneath where the CO2 was because it was much warmer. So if the oxygen can't get to the flame, the candle's going to go out because it's being smothered by all of the carbon dioxide in the beaker. Now the same effect happened on the second candle, but because this candle is much shorter, it was able to use the oxygen that was close to this flame that couldn't have made it to the taller flame. So in this case, the density had to do with the temperature difference between the carbon dioxide gas and the oxygen gas, but we were able to see these candles go out at different rates because of that effect.